Hello, this is a demonstration of conditional probability as set out in the MEI S1 syllabus, and I'm going to use January 2010 question 3 as an example. Just quickly looking at it there, you can see it's a three-part question in which they're going to ask us to create a Venn diagram with our probabilities in. Then they're going to ask us to carry out an independence test in part 2 on 2 events, and finally a conditional probability. We can see it's conditional because it's probability of R with a straight line for given G. Okay, so let's have a bit more of a read through this question. In a survey, a large number of young people are asked about their exercise habits. One of these people will be selected at random. So that's our equal chance of 1 out of however many, 1,000 or whatever, with these probabilities. So we're just going to use the probabilities they give. Okay, what are our events? Well, G is the event that the person goes to the gym. R is the event that the person goes running. So we don't know whether they're independent or not. These are just two things. You could do both, you could do neither. Then they're giving us some numbers here. So a probability G, so that's probability of going to the gym in this group of young people, is 0.224. Probability of going running is 0.13. And finally, the probability of going to the gym and running is 0.06. So that symbol there, which is the intersection symbol in set theory, is the one we use in probability as an and. So anytime we see it's going to be here gym and running, then we know it's the intersection. So let's have a look at part 1 and what they're asking us to do. They're asking us to draw a Venn diagram showing the events G and R and fill in the probabilities corresponding to each of the 4 regions of your diagram. Okay, so let's have a go at that. So let's draw our Venn diagram. Yeah, move it down. Just leave those up there. The probabilities so we can see them. So here's our Venn diagram. We have to draw the space. We have to draw, we've got here 2 events. So we've got 2 circles, and those are the sets in effect of the people who go to the gym or go running. So the one on the left here, it's important we mark them. Here is the set. This yellow line represents the set of people who are going to the gym, and on the right is our running. R marked with an R is our set of people who are going running. So what information have they given us here? Let's have a look. The first piece of information they've given us, so the third and most useful one here against these 4 regions, is the probability that you are going to the gym and running is 0.06. So we know that that is the intersection area. There's our 0.06. because that's a group of people, a subset of people who go to the gym and go running, yeah, because that's the intersection of the 2 circles. Okay, using a bit of colours now, they told us that the probability of going to the gym up here was 0.24. So here's our, I'm just going to mark the gym with the G in green. So that is the set of people who are going to the gym. And we know that the total of that is 0.24 is the probability. We've already attributed 0.06 for people who go to gym and go running. So that means everybody else doesn't go running. So that will be our 0.18. Yeah. So those 2 added together will give us our 0.24. So I found the 18 by taking 0.06 away from 0.24. So that was that side. Now let's have a go on the red side. On the right hand side is the runners. Well, they told us that 0.13 is the probability or proportion of people who go running. We've attributed 0.16 to and go to the gym. So the other 0.07 are the ones that don't go to the gym. So there we are. We've got 3 of our 4 areas, and we know that all the rest of the probability, total probability must add up to 1, so all the rest must not go to the gym or go running. So if we just add up our probabilities we've used so far, 0.18, 0.06 and 0.07, they add up to 0.31. And as we know the total is 1, we can take the probability away from 1, and we're going to get 0.69 is the remaining probability of that they don't go to either the gym or running. So there's our 3 marks there for creating our Venn diagram. Yeah, we got marks for entering the right initial probability for the joint, then for doing the calculations of the other 3 probabilities. And you've got marks to make. You had to make sure that you marked your 2 set circles as G and R, so it's very clear what you were doing. Okay, on to part 2. Determine whether the events G and R are independent. Okay, what sort of independence events have we seen in the past? Well, think about tossing a coin, thinking about rolling a dice. If and they are independent events, and we know that we can multiply the probabilities down the tree. So in general terms, and we'll use the events we've got here, if G and R are independent, then we know that the probability of G and R taking place should just be the probability of G, which will be the first part of our tree diagram, times the probability of R, because these are 2 independent events. Yeah, so that is our test for independence. What figures have we got here? Well, they gave us the probability of G and R up here as 0.06, so let's just write these out. Probability of G and R, we were told in the question, was 0.06. Yeah, and if we carry out so that's our left hand side sorted out. If we sort out our right hand side now, the probability of G times the probability of R equals, we had 0.24 times 0.13. Those are our 2 figures up the top. To go back so we can see them. So it's 24 and 13. So we're just multiplying those 2 together, the result of which is 0.0312. So the left hand side does not equal. So probability of G and R occurring in practice from the figures we got does not equal the probability of G times the probability of R. Therefore, G and R are not independent. Yeah, simple as doing that. You get 1 mark for knowing the process that you're going to follow, so by writing out the equation, and it's a method mark, and you get 1 mark for carrying that out correctly. Not particularly difficult thing to do. Okay, let's go on to part 3, which are conditional probability. Find the probability of R given G. So what does that mean? That's the probability that event R takes place given event G has taken place. Best way to think of it is it's actually taken place. Yeah. Okay. So we're going to do this 2 ways, and I'm going to rewrite the Venn diagram so that we can use it on screen. So I'll move down and get it set up. Okay, here's our our Venn diagram on the right and the probability we're trying to find on the left. So that's the probability of R taking place given that G has. And the important thing about the fact that it's saying given that G has taken place is that actually we're not interested in any part of this diagram where G does not take place. So I'm just going to put a red line through those sections that we're not interested in, because we're actually only left with the area of the set that we're in just here, which is G, yeah? And we've only got two probabilities left within that. And what we're asked to find is what's the probability that it's R within that set. Well, that area here we found earlier is this middle section. I'm just going to highlight it a bit more. So that section there is the probability that both G and R have taken place. So the probability of that happening is 0.06. And in the area of probability that G has taken place, well, that's all the probabilities let in within this space. So if we were just using the diagram here, the Venn diagram, we know that the total probability in here is 0.18 for going to the gym but not going running, and adding to that the probability of going to the gym and going running. Okay, which is going to bring us back to 0.06 over 0.24. The 24 you might recognize from the start of the question, where they told us that the probability of going to the gym was 0.24. That simplifies as fractions as 1 over 4, 0.25. So that is a way of using our Venn diagram to give us our answer. We can also do it using a formula in the formula book, which says that the probability, I'm just going to rewrite it in terms of G and R, but in the formula book it uses A and B. So the probability of G taking place given that R has is the probability of G and R taking place, which is logical, isn't it? Because they've said what's the probability of running and going to the gym, and divided by the probability of, I'm sorry, I've written this the wrong way. So my correction here, probability of running given that you're going to the gym will equal, and the probability of running and going to the gym, a person goes running and goes to the gym, that's what we've got on the top, divided by the probability that they go to the gym. Okay, so it's that way round. Apologies for saying it the wrong way round just now. Now, probability of running and going to the gym from our overall Venn diagram is 0.06, and the probability going to the gym, they told us in the original question, was 0.24. So we got exact same numbers we had from the graphical solution with the Venn diagram, and that brings us back to 0.25. Okay. So you've got two ways of doing it, depends how comfortable you are with either, but they will bring you back to the same solution and the same numbers. You can either use the formula or you can use the Venn diagram. Here's my little summary of conditional probability. We got the formula in the MEI formula book. I've written it here as it appears. So we've got our, what's the probability of A occurring given B has? So that's probability of event A given that event B has happened. And in the formula book, that'll show you that that's the probability of A and B happening. That's the intersection of the two divided by the probability of B happening, because we've restricted ourselves to that area. Two ways of doing it, depending on what sort of question you're looking at. You may have a question with a tree of events, and in that circumstance, I would suggest you mark in green, as I've done here, the arms of the tree that interest you, and you cross out the other ones that you're not interested in red. That makes it pretty clear what you're up to, and then you can work out the figures from that, the probabilities, if you want to do it graphically. And the Venn diagram follow a very similar approach. You can mark up the area of the diagram you're interested in and cross out in red, say, the areas you're not interested in, so it's really obvious, and then do your calculations. Remember, it's not necessarily just going to be one set as we've got here, the whole of G. In some occasions, it might be two areas there with the A not B and B not A. It might be that they're given that they're not the same, might have been the question. So it doesn't necessarily, you need to decide that and mark up the correct areas. So as I say in there, mark up in green the areas you're interested in, cross out in red the areas you're not interested in, or leave them unmarked. Finally, for an independence check, the real fundamental question is, does the probability of A and B taking place that you've been given or have derived from your Venn diagram, does that equal the probability that A times the probability of B, which is what you would be looking for if they were independent, like a dice, like a coin. You get the probability for the first part of your tree and you multiply it by the probability for the second part of your tree. That sort of principle. If they are the same, then they are independent. If they're not the same, then they're not independent. There you go. I hope that's of use to you, and good luck for the future.